Yeah. All right, well, here we go with the second half of chapter 11. So it's entitled Vibrations and Waves. We talked about vibrations last time. And so we'll talk about waves and this phenomenon called resonance tonight, which is really interesting. So hopefully we're going to be able to get something resonating, and you can help me out with that a little bit. So I'm going to drift down and take a look at a couple of things. So the quiz for this chapter has already been posted. And it is totally fine with me if you even have it open while we're doing this process. So we left off with the simple pendulum, and this features a restoring force, which if the angle is small, the restoring force is just minus mg theta. Now, the key thing about a restoring force is that it's negative, and it depends on the displacement. So that means it's always trying to make the displacement zero, which is great. But the key idea about that is that the force diminishes to zero when the displacement is zero, so it's never able to do the job. The pendulum swings back to its equilibrium point, but at that point the force is zero, so it just coasts right on by. So even though it's always trying to bring it back to equilibrium, it never can be successful, and that's why it's key to simple harmonic motion. Now, there's the formula, surprisingly, doesn't depend on the mass and doesn't depend on the angle, but it does depend on the length. So you have a question on the quiz about trying to find the length that has a period of exactly 1 second. And grandfather clocks famously have pendulums just like that. That's why they have to be so long. There are other ways to get around that requirement, but yeah, that's the key about the grandfather clock. Okay, well, the resonance piece we're going to talk about later. And but you already have a sense about what resonance is, just based on your experience on a swing set. Hopefully you've had that experience either as a child or maybe an adult pushing a child or something like that. The key about the swing is that if you wind up trying to get yourself going, that you have to swing your legs back and forth. You have to pump your legs back and forth. And as a child, we learn to do this ourselves, and we learn that the rhythm in which we pump our legs back and forth has to match up with the period of the swing. And that's called resonance. Very little effort can create a very big motion. All right, well, we'll talk more about resonance in a minute, but let's get to the wave motion. So we have a bunch of oscillators, but they're all connected to each other. That's the key idea here. So when you vibrate one, they vibrate their neighbors. And based on the proximity of the neighbors and the strength of that bond between them, that'll impact how fast the wave travels. So that is a surprising result for a lot of people, because initially a misconception will be that the speed of the wave will depend on how fast you shake it. But the speed of the wave is actually a property of the material it's traveling through, not based on what you do. So for example, you can't if you're out kayaking, you can't make the water waves go faster. You can make them bigger, but you can't make them faster because that's a property of the surface of the water. So what is a wave, and what's getting transported? What is traveling with a velocity? What's traveling is vibration, which does correspond to energy. So you have to put energy in, and energy travels along the wave. If there's friction, or damping is another word for it, then that energy can dissipate. But if there isn't any damping, then the energy can travel a very, very long way. So here are characteristics of our wave. Wavelength is the distance it takes for a wave to repeat itself. Amplitude is how tall it is as measured from the equilibrium. So it's not crest to trough distance, it's just from the equilibrium point. And then frequency and period are related to the wavelength through speed. And this is kind of interesting, so let's think about the units for this. Since the waves travel with a constant velocity, our good old-fashioned formula, distance divided by time, still works to calculate velocity. But also, I have to excuse myself for a second here. All right, sorry about that. The product of wavelength times frequency has units, so this is in meters, and frequency is in cycles per second. So actually, we could probably rewrite units for wavelength as meters per cycle, and then frequency cycles per second, and then we get the resulting units of meters per second. Two different kinds of waves, longitudinal and transverse. So transverse starts with T, and you can kind of see the T shaping up here, vibrations that are perpendicular to the direction the wave travels. And with the longitudinal wave, the vibrations are parallel with the direction that the wave travels. A good example of those are sound waves, where a speaker vibrates back and forth and creates compressions and rarefactions that result in changing pressure, essentially, and then your eardrum will respond to that. This is an interesting kind of wave. Water waves are actually kind of a hybrid of the two because it resembles a rotation. If you throw a stick in the water and send a dog to go get it, as that stick is bobbing up and down, you actually notice that it kind of makes a circle as it rotates. And then the speed of the wave changes based on the depth of the water. The bottom can actually act as extra friction, which will slow the bottom of the water, and that's why they break at shore. So intensity is not as important until we really start talking about sound. So I'm going to leave that out of this for right now, but it does follow the inverse square law, because essentially the energy is getting spread over a bigger and bigger area if we're operating from a point of view of spherical waves. So what happens when waves hit a boundary? If the boundary is fixed, then the pulse gets inverted. But if the boundary is free to move, then the pulse comes back upright. Now we're going to see the importance of that shortly. We also see when there's a change in the velocity of a wave that we see partial reflection happening as well. So we have a light rope where we assume that the speed is going to be pretty fast, and then a heavy rope where we assume that the speed is going to slow down. Reflection and transmission, you know, when we talk about waves, are they traveling in straight lines, or what exactly is happening here? So if we do happen to draw a wave as a ray like this, we would be talking about the direction that the crests are moving. So it's just a different way to represent waves. Now superposition is very important, and then this is going to actually lead to the short experiment we're going to do. So we have pulses far apart, and they're in two different directions. So what happens when they meet? Superposition says that what you get when two waves meet is we get the sum of the two. And that is interference that could either add together or cancel out. So these two inverted pulses will cancel each other, but the two pulses in the same direction are going to add together. So let's take these two waves. They look like they're in sync with each other. So when we add them up, we get a bigger wave. It kind of makes sense. These two pulses are exactly out of phase with each other. It means phase means one goes up, the other one goes down. They are out of phase with each other. So when we add them together, they cancel. And if there's some weird kind of phase, then we just get a mix of the two. So let's go ahead and take a look at the standing wave phenomenon. I'm going to pull up a simulation that I've got running. And we can generate pulses. And I've got some controls down here. So I'm just going to generate a pulse. And shoot that pulse down. And you can see it's oscillating back and forth. Now this is a fixed end, so that's why it inverts, and the other end is fixed as well. So if I went to a loose end like this, to kind of picture what that looks like, you can see that's why the wave doesn't get inverted there. And if I get no end, then it just goes out the window. Yay. But what I'm going to do is do a little experiment here. So This would be a good one for you to jot down. We're going to let this run for 10 back and forth. So we see that the length of this is about 7.5 centimeters. We're going to narrow up the pulse a little bit so it's a little bit sharper, easier to keep track of.
I think you could also share the link to this in chat.
Let's see. That show up all right?
Yeah, thanks.
Yeah, you bet. All right, so we're just going to run a quick experiment. I'm going to let it go down and back 10 times, and then we'll find out what the velocity is. Okay, so here we go. We're just going to time it really quick. I'm going to start a pulse, and then when it comes back, then I'm going to start the timer and start counting. So 1, 2, 4, 6, 8, 9, 10. Okay, so I get about 11.79 seconds. Might have been a little late there, but let's go with it anyway. So the total distance traveled, that was 10 lengths of 7.5 centimeters. So that's 75 centimeters divided by 11.79. And we'll see what we get for a speed. So I got 6.36 centimeters per second. And I'm putting this on my document camera, so we'll switch over here in just a second. Okay, now what can we do with this? Well, here's the thing. If we can take a look at this notion of standing waves, what makes standing waves is that we have waves that are trapped on this string and just go back and forth, and they start to interfere with each other. We have waves that are traveling from left to right, encountering waves, reflected waves that travel from right to left, and they interfere with each other. Now that interference could be kind of chaotic, but if everything is at just the right situation, we can actually get resonance to happen. So let's see what that looks like on our simulation. I'm going to switch the pulses. I'll let this one out the door first. Bye. We'll go back to a fixed end, and I'm going to change this to oscillate. I'm going to back off on the amplitude a little bit. Also, one way to kill the waves is to just crank the damping briefly. Okay, so this is just kind of chaotic. We don't really notice anything in particular. Sometimes you might notice if you pick on a particular green dot, you'll see that sometimes it almost stops, and then sometimes it moves a lot. So this is a little bit chaotic because we have waves traveling from left to right, interfering with reflected waves traveling from right to left. Now, let's do a little bit of work here. One of the things that we notice is that with a wave on a string, the speed is determined by the tension and also determined by the linear density. I'll do a sample program problem later on to just show that. But here's what my my experiment is going to look like. I'm going to stop sharing just for a minute, and then I'm going to change my video source so you can see my whiteboards. Can you see my whiteboard?
Mm-hmm.
Okay, great. So what would be interesting is I'm curious about these two endpoints. And if I could generate a standing wave, and you'll see what they look like in a second, a standing wave of one wavelength would look like this. So here would be one wave interfering with another wave that's coming the other direction. So in some places, they're going to cancel each other out, like here. And in other places, they are going to add together, like here. Now, this is called a node, N-O-D-E. And then this is called an antinode, a place where it vibrates a lot. So there, on this standing wave, there are going to be two antinodes. So I'll just do a little direction here, antinodes.
Mine's a little fuzzy. Is anyone else's fuzzy?
Let's hit a little
Yeah,
focus.
Yeah.
Mine's having, no, there. Yeah, you almost got it. That.
Better? Not better?
Yeah, that's perfect.
Okay, great.
That's even better.
Okay, yay. And these are nodes. Thanks for speaking up, though. Woo. Anatomy of a standing wave. I don't know what happened to Uncle Node, but those are antinodes. All right, so let's see if we can make this happen. Now, I'm curious that if we know what the speed of the waves is, and we know that the wavelength is equal to 7.5 centimeters, then that should tell me what the frequency is. So frequency equals speed divided by wavelength. Do this on my calculator. So I have the speed left over from the last calculation divided by 7.5. And that gives me a frequency of 0.848 hertz. Now let's see what happens in our simulation if we plug that in. I'm going to change video source and then go to share. Okay, good. You have the simulation? Somebody just go, yay.
No. Oh, there we go.
Yeah, okay, good. I'm going to adjust the frequency then and see what happens. And also, just to emphasize this, I'm going to just make a very small amplitude, just little tiny vibrations. I'm going to let these out the window, the leftovers. Goodbye. And now the frequency I need is going to be 0.84 or about, let's see how close I can get. Like I can't do direct entry into that window. So we'll get as close as we can. We're going to shoot for 0.85. Okay, now here's something interesting that's happening. So we can get an idea about pulling up and down by looking at this wheel, right? So we can see a very small oscillation happening here. But it's happening at just the right moment. So when the wave is down, it pulls up. When the wave is up, it pulls down. And you can see that we're getting an increase, but there's a place that hardly moves at all. And that's a node right there. Here's a place where we get lots of movement. That's an antinode. And so now we have a standing wave. It looks like a wave if we pause it in time. It looks like a
By the
wave.
way, if you really want 0.84, just click the left arrow next to the frequency.
Well, let's see. I think I jumped the gun on the timing a little bit. So I'm guessing it actually might be something more like 12 seconds. So that would make my speed a little too fast. And if my speed is a little too fast, that means my frequency is probably a little on the high side. So yeah, we can try this and I'll let this go. But I also, in the interest of time too, I don't, let's let this out the window. Goodbye wave. So you can see it flat. So this is actual how big our wave is that we're putting into it. It's very small. But as soon as I clamp down on this fixed end, then resonance will start to build up. So resonance, by definition, is putting in just a little bit at just the right frequency. And since it's at just the right frequency, we get a really big impact. And if I just increase the amplitude a little bit, then we'll see that really taking off. So I think this is actually a little bit better than what we did last time, because this center dot is really hardly moving at all. Now, if that's the case, then let's look for another frequency that's going to cause resonance. So I'm going to take, we're just going to go with 0.84, and I'm going to call this F2, and I think you'll see why in just a second. Look at that go right now. That's pretty crazy, isn't it? Okay, now let's try something really quick. I'm going to stop sharing and then go back to my whiteboard really quick. Okay, I'm going to call this F2 because there's two antinodes. That means that F1 would be half that. So that would be 0.42 hertz. And F3, if we were going to get three antinodes, would be 3 times that fundamental. So I'm going to go 0.42 times 3, and that gives me 1.26 hertz. So we sort of have a family of frequencies happening here. 0.42, 0.84, 1.26. Let's do one more just for fun.
1.6 again?
Could you say that a little bit louder, please?
How did you get 1.26?
I multiplied the first frequency, F1, by 3.
Oh, okay.
So this equals 2 F1. This equals 3 F1. And then this 1.68 hertz is equal to 4 times F1. All right, we're going to go back to the simulation and give it a go. So let's try that fourth one. I'm going to go to 1.68. So pull it up. We'll let the old waves out the window. See you later. You can see our input wave is wiggling with a higher frequency now. And we'll see how long it takes before we start to see resonance. So this is a higher frequency. We still get resonance out of it. Again, resonance is inputting a very small signal, but at just the right frequency and getting a big result. This will become really important in our next chapter in sound, because that's what our musical instruments do. They resonate. They're designed to resonate at particular frequencies, and then each instrument has its own characteristic way of changing that resonant frequency. Yeah, so this is much faster, and just for fun, let's see what our fundamental would look like. I'm gonna pull our frequency way down and get to the 0.42, and let's see what that looked like. Out the window. Woo. Right, again, so this is our fundamental frequency. This is F1. And you can see very clearly that when the wave is high, it pulls down. When it's low, it pulls up. And so this, again, is an example of resonance. A very small input gives us a very large output. So let's go back and take a look at our slide deck then. Standing waves and resonance. Our first harmonic or fundamental frequency gives us a standing wave that just has one antinode. 2 times that is going to give us 2 antinodes. 3 times that is going to give us 3 antinodes, but all these frequencies still get this single string to resonate. So we have a family of frequencies and wavelengths that cause this, this object to resonate. So we're going to hold off on the mathematical representation, but that's a good wrap up. And I did want to do one practice problem before we run out of time. And so I'm going to go back to my whiteboard. Look at how fast I cleaned that one. It's not amazing? Okay, so here we go. I'd like to do a quick example that has to do with the speed of a wave on a string. So here's our string. And we know the speed. We know this because I'm telling you right now. It wasn't in the slide deck. But the tension of the string divided by the linear density, this would be kilograms per meter. And if we take the square root.
Sorry.
Yep. No problem. Thanks for letting me know. Is
There
that
we
better?
go.
There.
Yes,
All
there you
righty. Good. So we're going to generate, let's see, let's suppose I wanted to create resonance on a string, and I wanted to find the fundamental frequency. So I have to be given a couple of variables to work with here. And let's suppose that our tension is equal to, well, maybe it's a guitar string, let's say. And maybe the tension is equal to 200 newtons, right? So we know that that's what the tuning screws do when we crank, it changes what the tension is to get just the right note. And let's suppose the linear density is something like, well, on guitars, they're all different linear densities, right? So they could be different things, but let's suppose it's one of the big thick ones. And so maybe it weighs something outrageous like 7 grams per meter. But we're of course going to want that in kilograms per meter. So that's going to be 0.007 kilograms per meter. Okay, well, why don't you go ahead and calculate what this velocity is, and I'll do it at the same time, and let's see if we wind up agreeing. So the tension divided by the linear density, and then take the square root. I get 169 meters per second. That's cruising. How'd you all do? Did you get something similar?
Yes.
That's great. Now F1 is going to be a standing wave, and we have to assume some kind of length. So let's suppose the length is equal to, I don't know, 70 centimeters.
I should probably mention that we have a minute left.
Okay, okay. Thank you.
If you run out of time, you can just log back on using the same code and you'll be fine in 10 more minutes.
Okay, sounds good.
All right.
Let's go ahead and just let it expire then, right? Where's my countdown?
For us, it's on the screen.
Yeah, okay.
Yeah, so you can just log on using the same code and the same password and everybody should get right back on. It should be fine.
Okay, so if not, then I'll send a message in Canvas for a new code.